All right, welcome back. We're moving on to section 10.5, which is called Existence and Uniqueness. But I have in parentheses here Picard Lindelof, and that's because these two names, it was two people who kind of came up with the proof of when we would have existence and uniqueness for some nonlinear problems. Their names are synonymous, basically, with the theorem which proves existence and uniqueness. So a lot of people, especially mathematicians, will just reference Picard Lindelof or Picard Lindelof theorem, and you're supposed to interpret that as meaning the existence and uniqueness of nonlinear ODEs. And why is this even a question, right? So this doesn't actually become a question until we run into nonlinear ODEs, because it turns out that it's somewhat trivial to prove existence and uniqueness for linear ODEs. But now that we're in nonlinear ODEs, we do actually care about these. So we'll start here with a nice example where we're looking at the initial value problem. Y prime is y to the 1/3 power, and at 0 it's equal to 0. And I'm going to present the following as a possible solution. Okay, so I'm just, we don't have necessarily a way of solving for this solution yet, but I'm just going to present, hey, I'm claiming this is a solution, let's verify it. So we take a derivative, we end up with 2/3 t to the 1/2. Similarly, if I decided to take a cube root of the solution that I claim, I also end up with 2/3 t to the 1/2. So we definitely have that the derivative is equal to the cube root. Okay, derivative is equal to the cube root. Let's verify that if I plug t equals 0 in here, plugging in t equals 0, I do end up with 0. So indeed, this is a solution to the initial value problem. And then we move on to a second example, and we have this initial value problem, y prime equals y to the 1/3, and y at 0 is equal to 0. And now I'm going to claim that for all times, y equals 0 is a solution. And we can verify this by computing a derivative of 0, and we get 0. We take a cube root of 0, and we get 0. And we also evaluate the function 0 at the time 0, and we get 0. And so we satisfy the initial condition, we clearly satisfy the ODE as well. Okay, so 0 is a solution to this ODE. But of course, all of you have probably recognized this by now, that the initial value problems were the exact same. This is the exact same initial value problem as the one I have here, and yet my solutions, which I have here, are not the same. Right, so we have two solutions to the same initial value problem. And so if you ask yourself if this initial value problem represents a physical system, and I'm trying to predict the future about this physical system, and I solve my initial value problem to try to predict the future, if I have two possible solutions, how do I know which one is the right future? So that's kind of a bad thing. This is kind of an unfortunate situation that we've run into where we have two possible futures to any given present. And that's, if we're trying to truly predict things, obviously possible futures is philosophically a problem that we can actually tackle. But assuming that we want some sort of deterministic future, then this is kind of a bad situation. So we might want to know a little bit more about what are the good situations, what are the bad situations. Obviously, in this setting, we weren't running into an existence problem, we were running into a uniqueness problem, right? The uniqueness of the solution of the IVP didn't exist. We had two different solutions. So this kind of harkens back to chapter 4, when I was, we just spent some time on functional equations, and we talked about how all of ODEs was really just finding the preimage of the constant function 0, right? The preimage of the constant function 0. And we said that preimage set did not necessarily contain only one element. And in this situation, where I guess, if we really want to write ourselves in the notion of chapter 4 notion, this is t equals d dt minus n, where n is the cube root operator. Right, this is the cube root operator. And in that setting, t of y is d dt of y minus y to the 1/3. And so then the question is, when is this equal to 0? You find the preimage of 0, and that's your set of solutions. But the set contains more than one element. And actually, you could throw the initial condition y of 0 equals 0 into the operator t. It would look like a delta function, or an evaluation operator is how you can think about it. But anyway, this kind of harkens back to that chapter 4 of saying, okay, we have these preimages which are sets, and we would like the set to have only a single element inside of it, but unfortunately, in a lot of situations, it has more than one element. Or sometimes it's empty and it doesn't have any elements in it. And either of those are possible problems we can run into, and that's the idea of existence and uniqueness. If you satisfy conditions, we say something about, oh, this preimage set has exactly one element inside of it. That's what we want to say. Okay, so maybe what we're trying to answer is, when does this set, also known as the solution set of the IVP, contain exactly one element? When is there exactly one solution? Existence means there's at least one. Uniqueness means there's only one. So let's just introduce that theorem. So the theorem's right here. It says given an IVP, also known as maybe my nonlinear Cauchy problem, possibly linear too, but given an IVP, so your generic first order IVP, and we recall that we can convert any higher order IVP into a first order one, you just have to increase dimension. But given the first order IVP, if we can compute the linearization, this is why I was introducing linearization, why we made such a fuss about it in the previous sections. If I can compute the linearization or derivative, however you want to interpret that, of my nonlinear operator at the initial condition, right? So notice that the y0 is derivative at y0, and the time is at t0, and those are both the entries of my initial condition. So if the linearization or derivative of my operator exists at the initial condition, and it's continuous, must be continuous at the initial condition, then there exists a unique solution on some time interval. This is the unfortunate part. Some time interval is somewhat vague, right? It says there's a very small, possibly a very small amount of time. It says it's finitely large, right? Like it has a a positive time. It's not infinitesimally small, but it can possibly be tiny. We can have like the solution stop existing really quickly after we've started. But it says if you wait, tiny enough fraction of time, we have a unique solution, right? So it exists and unique. So we have a unique solution. So this is really nice, right? Because this property is strong, but it's not out of this world strong. Like we would expect a lot of functions to have a derivative at the initial condition, and for that derivative to be continuous at the initial condition. If the right-hand side were something like cosine of y plus, y plus y2, that's some fixed vector t, something like that. That's a perfectly infinitely differentiable nonlinear function of y, right? So we'll be just fine there. Can't do plus there, just give you a dot product or something, dot product of those two. But you get the idea, and times y. You get the idea that this is a perfectly valid right-hand side to have, and the derivative exists and it's continuous at the initial condition. So we don't run into this problem that often, but it's something to keep in mind, and it's also something that's really easy to check for, right? We can check for this to occur, and I'm gonna scroll down to the example of checking for this to occur before getting into some other theorems. So we can check really easily for this to occur. What is the derivative of the right-hand side here? Well, the derivative, let's say d at, notice this is y naught, right? So d at 0 of y to the 1/3, that's the partial derivative in y of y to the 1/3, evaluated at 0, gives me 1/3 y to the negative 2/3, evaluated at 0, but a negative exponent is actually a denominator, right? This is 1/3, 1/3 y to the 2/3 at 0, and all of a sudden you see we have 1 divided by 0. And so we fail the Picard Lindelof theorem. Fails Picard Lindelof at initial condition. And this is exactly, this isn't why we see two solutions, but we know that it must fail Picard Lindelof because we had two solutions. So obviously the way theorems work, if we fail Picard Lindelof, that doesn't mean we don't necessarily have a unique solution, but it means that you can't guarantee that we have a unique solution. So Picard Lindelof is failed in this case, and that's a bad thing, right? And so if we jump down maybe to the next problem here, we're looking at a vector value problem, and we look at the right-hand side of that vector, and we want to linearize it, take the linearization at the initial condition, which in this case is 1, 1. And if we decide to represent the bilinear operator maybe as this is another way of representing an array, because basically we have a matrix of a matrix, right? Matrix of two matrices. Then you can compute the derivative pretty easily. This is just the product rule on these two terms. I maybe should have written it more as a true product rule, but there's the 2 out front because the matrix is equal to its own transpose, and so you're good to go there. I do have a typo here. This should be a 1 there and a 0 there. I have it correct in the bottom term. But anyway, if you compute the derivative or the linearization of the nonlinear operator on the right, and you recover the following, which I can evaluate at y0, which is the vector 1, 1. So if I evaluate this at 1, 1, and 1, 1, then I end up with the matrix 0, 1, 1, 0. Right? And so this matrix 0, 1, 1, 0 is definitely well defined, and it's definitely continuous because it's constant. All constant functions are continuous. So that's a constant function, matrix value function. So it's continuous at the initial condition, and it's certainly defined at the initial condition, the linearization. And so we know that we have a unique solution, which is the next comment. So yes, so that's what I said. The solution exists and is unique, right? So we know it exists and it's unique because we can compute the derivative or the linearization at the initial condition. We get something that's defined and continuous. And so that's Picard Lindelof in action. And then we should look at a few, really the proof, and then a couple of corollaries, because it's also a very useful result that Picard and Lindelof have had because of the way that they prove this. So the proof relies on the fact that if I consider my initial value problem here, and I integrate both sides. Let's integrate both sides. What I get is, on the left-hand side, that the integral of the derivative is just the endpoints, right? So this is yt minus yt0 equals, and then on the right-hand side, the integral from t0 to t ns y of s ds. And then if I rearrange that, I recover the following. Yt equals y at t naught plus the integral t naught to t ns y of s ds. Okay, so that's this. The right hand side that I just computed was also the thing that I circled in the notes. So that right hand side and this right hand side are the same, except for the fact that we'll do the pen in red, except for the fact that the input here versus here the input on the right is the same, right? It's more like the y on the left-hand side and the y on the right-hand side are the same function. On the left here, what I've done is I'm iterating. I'm saying we're going to start at the initial condition. And then I'm going to define a recursive sequence, right? It defines a recursive sequence. And then if I take the limit of that recursive sequence, I actually recover the unique solution. So this is a little bit interesting, right? So what Picard Lindelof have done, and really this is really Picard's approach to the problem, is he defines this recursive sequence, which in the limit, as you compute infinitely many recursions on this sequence, you actually recover the true solution to the IVP. And this works for nonlinear IVPs, which is incredibly useful, right? So this recursive sequence is very important, and that's where the corollary shows up, where it says the fixed point solution to the nonlinear Cauchy problem. What the corollary says is I can solve a nonlinear Cauchy problem. So here's the nonlinear Cauchy problem. I can actually solve it in a limiting procedure using this sort of behavior, which I defined above, right? This is me just integrating both sides and adding the initial condition. So if I define that as an operator J, it's a nonlinear operator. Right? This is a nonlinear operator. But I just defined that operator on the space of functions f, however you want to think about it. But it maps the space of functions to another function. If I compute infinitely many iterates, so powers of this operator, I'm composing the operator with itself. So compose the operator with itself infinitely many times. So we're just going to compose that operator with itself infinitely many times. I didn't write j to the infinity power because that's maybe poor math notation, but you want to think about this as like j to the infinity power of the initial condition actually solves the ODE. It solves the IVP. So an infinite power, infinite compositions of this operator solves the initial value problem. That's what's nice about this corollary. It's actually incredibly important for ODEs in general, this notion right here of Picard iterates. And so then the next definition, what I have here, is what we call the Picard iterates, and this is just a finite power of that operator that we would want to take infinite powers of. We just take finitely many powers of that operator, and what we get is what we call the Picard iterate, or the nth Picard iterate, when it's an n here, the nth Picard iterate, and this will be an approximation to the solution. So this is one way of constructing approximations to solutions. And this is maybe the easiest approach to approximations of solutions, because it's not that hard to tell a computer how to implement something like that and just have the computer iterate over it 10 times, you're going to get something really close to the actual solution. Anyway, that's all I have. I'll see you in class. Bye.